Today we're going to take a look at writing formulas, and you'll be able to compare how writing formulas is very similar to naming compounds, but you apply those same rules just backwards. You're still going to need to know your oxidation charges for everything in groups 1 and 2 and then groups 3 through 8. You'll also need to know your polyatomic ions over here on the right-hand side of your polyatomic ion list. Some other things that we'll be looking at when we when we write formulas are how to write formulas of molecular compounds, which means they have been covalently bonded. So we'll be using these Greek prefixes for that. And we will also take a look briefly at acids and bases. So let's get started with writing formulas. Remember when you write a formula that the charges in the formula have to add up to 0. So what do we mean by actually writing formulas? What I mean is taking the name of the compound, such as magnesium sulfide, and coming up with the elements symbols from the periodic table and how many of each atom you would find in that compound. Remember that these ratios are constant. They're always found in the same ratio for each compound. So to do this, you look up the charges on any ions. These would simply be for ionically charged compounds. So ionic compounds, things that are bonded through ionic bonds. You'd have to find the charges on each ion. The cations come from the name on the periodic table. So these are the metals. These would be in groups 1 or 2. And the anions may either come from the periodic table or from your polyatomic ion list, which I have shown here. And then you simply balance the charges by adding the subscripts. And remember that polyatomic ions, put those in parentheses if there's more than one of the polyatomic ion. And I'll show you how to do this. Things to look for. If the cation has a parentheses and a Roman numeral in it, that means that Roman numeral is the charge for that cation. It's going to be +3, +2, +4, something along those lines. If the anion ends in IDE, that means it's straight off the periodic table, and you can simply look at the oxidation number that's given here and use that as its charge. If the anion ends in ATE or ITE, it's probably a polyatomic ion, and you'll need your polyatomic ion list to give you the charge for that particular ion. So let's take a look first at calcium chloride. If we look at our oxidation numbers for calcium and chlorine, calcium is in group 2, so found here, has a +2 charge. Chlorine, all the way over here, has a -1 charge. So remember, +2 and -1. If I were to write this out, I would simply write calcium, give it a +2 charge, write chlorine, give it a -1 charge. To write the final formula, you crisscross these charges. So the final formula becomes Ca, since the charge is -1 that we're crossing down to become this subscript, we don't write it. If there's only one of that atom, then we don't write a 1. Chlorine becomes Cl2. So to make this a neutral compound where all of the ions balance each other out, we have CaCl2. Calcium is +2, chlorine is -1. We need 2 chlorines to balance out the calciums, so we have CaCl2. And as a reminder, when writing the ions next to each other, you crisscross the charges, and that becomes the subscripts. Sometimes you'll need to reduce, just like a fraction, and I'll show you some examples of that just in a minute. So let's look at some formulas for a whole variety of different compounds. These are all ionic compounds. So if we start with lithium sulfide, we need to write the formula for lithium sulfide by first looking up the oxidation number for lithium and sulfur. I know that both of these are coming straight off the periodic table. Lithium is not a transition metal, and sulfur ends in IDE, so it's not a polyatomic ion, which means I can go to this chart for both of them. Lithium is a +1, sulfur is a -2. So remember, lithium +1, sulfur -2, and let's write this formula. Lithium is Li. We said it was +1. Sulfur is a -2. If we crisscross the ions and rewrite, we have Li2S as our final formula. Let's clear the board and take a look at the next one. Tin 2 oxide. Okay, I have something in parentheses. So that tells me tin 2 oxide. That means tin's element abbreviation or symbol is SN. So that means that has to be a +2. Oxygen is a -2. So crisscross 2 and 2. Those cancel each other out, and we don't have to write any subscripts, so we get SNO as our formula for tin 2 oxide. Tin 4 oxide is a little bit different. Tin 4 oxide, tin 4 is going to be a +4. Oxygen is still a -2. If we crisscross our formula, or crisscross our oxidation numbers, we get SN2O4. But if you notice here, these two can be reduced. They can be both divided by 2, and so our final formula becomes SNO2. Reduce if you can. Okay. Moving on to magnesium fluoride. All right, magnesium and fluorine are both in our oxidation number chart. Magnesium is in group 2, so it's a +2. Fluorine is in group 7, so it is a -1. +2 and -1. Magnesium +2. Fluorine -1. Crisscross. And rewrite. Magnesium, fluorine. Magnesium, or MgF2 is our final formula. Taking a look now at copper 2 sulfate. Copper 2 is a transition metal. Fortunately, we don't have to figure out its charge because the Roman numeral tells us what it is. Sulfate. Sulfate is not off the periodic table. This is a polyatomic ion. So let's start by writing copper's symbol is Cu, and we know this is going to be a +2. Now we need to go figure out what sulfate is. So I'm going to look on my polyatomic ions, sulfate, all the way down at the bottom. Sulfate is SO4, and it has a -2 charge. SO4 and a -2 charge. Fortunately, the two charges balance each other out, so all I have to do is write each of the two components of the compound, Cu for copper and SO4 for sulfate, and I don't need to write any additional subscripts because +2 and -2 already balance each other out. Our next is iron 3 phosphide. Iron 3 tells me Fe will have a +3. Phosphorus is going to have a -3 charge right here. So crisscross, these balance each other out already. So we have FeP. Our next is gallium nitrate. Gallium is not one that I work with frequently, so I'm not even sure. I'll have to go take a look here at our oxidation numbers to find gallium. Gallium's not in group 1, not in group 2, not in our first transition metals. Ah, here's gallium. Gallium is in the +3 group in the periodic table. And nitrate is a polyatomic ion. So let's start by writing gallium +3, and then let's go find nitrate in the polyatomic ion list. Nitrate, NO3, and that has a -1 charge. So NO3 with a -1 charge. Crisscross our charges, and we get gallium, and then NO3 goes in parentheses because we're going to take that 3 times. So we have 3 nitrates. So the rest, iron 3 sulfide, ammonium chloride, ammonium sulfide, barium nitrate. Take a look at how these are written in terms of formulas right here. So iron 3 sulfide, ammonium chloride, ammonium sulfide, barium nitrate. Good. Now let's move into writing formulas for molecular compounds. These are things that are covalently bonded. Here we're going to look at both writing names and formulas. These are made of just nonmetals, so maybe you are combining carbon and oxygen. The smallest piece, the smallest piece of whatever these are called, is called a molecule as opposed to a compound. The molecules can't really be held together because of opposite charges, because we're not dealing with ions here. These are dealing with covalent bonds, which means they are sharing electrons, not transferring electrons. So you can't use charges to figure out how many of each atom you would have. This is actually an easier thing to write formulas for and to name. And here's where we're also going to go into using these Greek prefixes. Ionic compounds, we know, use charges to determine how many atoms of each there are. So you have to figure out the charges, and then you have to figure out the numbers. But molecular compound, the name just plain old tells you the number of atoms that you have. And you use those prefixes to tell you that number. So the prefixes are as follows, and yes, you need to know them. 1 is mono, 2 di, 3 tri, 4 tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. The only one we don't ever use is mono. So to write the name, you have to write 2 words. The one exception is that you don't write mono if there's only one of the first element. So whatever element comes first, if there's one of it, you just name it off the periodic table. And you kind of avoid double vowels when you write out the names. So you write a prefix in a name, and then a prefix in a name, and the ending IDE. So for example, N2O, this is nitrogen and oxygen. We have 2 nitrogens, so we call this dinitrogen oxide. NO2 is a little bit different. We only have 1 nitrogen and 2 oxygens, so this is nitrogen dioxide. Cl2O7 is dichlorine heptaoxide. CBr, this is carbon and bromine. So this is carbon tetrabromide. CO2, carbon dioxide. BaCl2 is barium and chlorine. So this is barium dichloride. And then when you write formulas, you basically do the same thing. Diphosphorus pentoxide, you look at your prefixes, di meaning 2, and pent meaning 5. So if we write out the formula for diphosphorus pentoxide, diphosphorus pentoxide. It's as simple as that. You don't need to worry about any charges. Tetraiodide non-oxide. So we wouldn't say nano-oxide because then we'd have 2 O's there and it'd be hard to pronounce. So you leave out the 1 O, non-oxide. If we were to write this formula, tetra means 4 and nano means 9. Sulfur hexafluoride, dinitrogen trioxide, carbon tetrahydride. I'll let you figure these out. Phosphorus trifluoride and aluminum chloride. One last thing to discuss when we talk about writing names and formulas for acids and bases. Acids are compounds that give off hydrogen ions. So remember, hydrogen ion would be a hydrogen plus 1 when they are dissolved in water. They have to have hydrogen in them. Bases, on the other hand, have to have hydroxide in them, so the OH minus 1 charge. So for an acid, it'll always be a number of hydrogen atoms next to some sort of anion. The anion determines the name. So the anion, for example, HCl, is what determines the name of that particular acid. If the anion is attached to hydrogen, ends in IDE, you put the prefix hydro for hydrogen, and then you change the "ide" to "ic" and add the word acid at the end of it. For example, HCl is a common acid that is found in your stomach. It's what breaks down and digests your food particles. HCl is a hydrogen ion and a chloride ion, so we call this hydrochloric acid. We have the hydro for the hydrogen, we add chloric, and then we add acid to the end. H2S is a hydrogen ion and a sulfide ion, so this becomes hydrosulfuric acid. And that's all you need to know in terms of naming acids, and we're not going to worry about naming bases. If you have any questions, please let me know.